In today's lesson, we want to talk about application problems, in particular what we call optimization problems, which involving solving problems with maxima and minima using basically the calculus techniques we've learned for dealing with those sorts of things. It turns out that maximizing and minimizing functions are one of the most common ways of using calculus in a practical manner. And so I just want to dive in and work problems today. We're just going to work problems, and through doing that, I hope you'll start seeing some general patterns emerge so that when you see a problem, a strategy comes to your mind because you've done so many similar problems in the past. So the idea is to build some kind of general strategy by practice and watching problems being solved and seeing the commonalities. Let's just dive right in. Before I get into a lot of the calculus, I want to start off with a more visual graphical example to sort of illustrate what the calculus, the actual nitty-gritty techniques, derivatives, and things like that are telling you in terms of the big picture. So what if we start off with this? We've got a graph that shows the profit in thousands of dollars of a company in terms of its advertising cost. That's the X variable, and that's also measured in thousands of dollars. And that graph tells us a lot about how the profit for that company is related to the advertising cost. I can ask any series of questions about this, but what if I ask you to estimate the interval on which the profit is increasing? Well, after what we've done up to now, that should be fairly easy. Increasing, when you're given the graph, simply means from left to right, the graph rises. And you can see that starts on the left at 0 and continues until it gets to a peak at 40. So the interval is just 0 to 40, the open interval 0 to 40. What about where it's decreasing? Well, that's where, going left to right, it's headed down. It picks up at 40, and then you think, well, maybe it goes down to get 60. Well, if you look very close at that graph, it goes a little past 60, so maybe to 61. We'll say 61. So the interval decreases from 40 to 61, and the open interval then would be the solution to that problem. Another question. To estimate the amount of money the company should spend in dollars on advertising in order to yield a maximum profit. Remember, the cost in dollars on advertising is the X value. It's the value on the X-axis. And we've already decided that happened right there, which is X equals 40. But remember, they said how many dollars, and the graph says that this is in thousands of dollars. So it's not $40, it's $40,000. So when you're translating things across units, you got to be very careful. X, in this case, was in thousands of dollars. So if you want to tell someone how much you need to spend on advertising, you're not going to say $40. You got to relate that back to the fact that you're measuring them in thousands of dollars. And how about this one? Estimate the point of diminishing returns. If you'll recall, the point of diminishing returns occurs at an inflection point where the concavity changes from up to down. If you look at this graph, you can see that as you start out on the left, the concavity starts out being up. Remember, you think of up as holding water. And at some point, it starts spilling water. That's concave down. And that seems to happen right about there, which is the point 20, 2000. So that would be the point of diminishing returns. Now let's do a similar problem without the graph. Suppose we have a profit function. P is given by this polynomial function with, instead of an X, it's got an S, but it works the same way. S is the amount of advertising in thousands of dollars, and we want to maximize profit, and that's also in $1,000. Notice it's very similar to the wording of the previous problem, but in the previous problem we were just looking at the graph. Here we don't have the graph, so we have to do more of the nitty-gritty work ourselves. Well, what's the first step? You want to take the derivative, set it equal to 0. Now notice when you've got a polynomial set equal to 0, one of the first things you want to try to do is get something to factor. And I noticed that there is an s in both of those terms, so I'm going to factor that s out. Now I can say when the product of two things equal to 0, that means either one or the other of them equal to 0. So either s equals 0 or negative 0.3s plus 12 is equal to 0. And if you solve that second one for s, you'll find out that s would be 40. So either s equals 0, s equals 40. Those are our critical values. But remember, we're actually going to produce something, so we're not considering 0 in real life as a practical answer, because you wouldn't even be in business if you produced nothing. So 40 is really the only critical number that we're interested in the real life context here. So you can neglect the 0 because you're going to produce something or you wouldn't even be in business. But if I want to be sure that it really is a maximum, sometimes you want to develop some kind of comfort level. I feel like 40 is the value that gives me the maximum, but I haven't actually verified it. Recall that the second derivative test, when it applies, is actually the easiest way to verify if something's a max or min. So if you really want to boost your comfort level up and say, yes, this really is a max, then you take the second derivative and plug in 40. Well, the second derivative polynomial is really easy to take. So if you get negative 0.6s plus 12, and if you plug 40 in, you get negative 12. Negative 12 is a negative number. That means the concavity is negative. If the concavity is negative, that means you're at a max. Remember, our second derivative test says negative concavity means max, positive concavity means min. So that little boxed work there is just something I did to increase my comfort level. I felt like 40 was going to be the max. Now I've verified and I'm certain it is. And the problem said to find s. Well, we found s. They didn't ask us how many dollars you should spend. If they said how many dollars should you spend to get maximum, it would be 40,000. Remember, it's in $1,000, but they didn't ask us. You have to be very careful. They just said to find s. They didn't say to interpret what s is. In dollars, it would actually be 40,000, but they just said to find s. You have to read the problems carefully and make sure you've answered the question that has been asked. Now, they can ask other questions. We know that 40 maximizes the profit, but they could say, just like in the earlier problems, what is the point of diminishing returns? But again, just as in the previous problem, it's an inflection point where the concavity changes from up to down. Talking about concavity, you have to do the second derivative. But the first derivative was simple, so the second derivative is simple. If you take the second derivative, you end up with negative 0.6s plus 12. Set that equal to 0, you get s equals 20. That's this s value right here. But we also have to find p. What is p? Well, to find p, you have to go back to the original function. That's where p is. So I plug in 20 into the original function. There's a little bit of calculation, but it's not difficult. You'll end up with 2,000. So the point of diminishing returns is the point 20 comma 2,000. Notice how similar that was to the previous problem we worked. The difference being, in the first problem, they gave us the graph and we could use the graph to answer those questions. Now, in this problem, they did not give us a graph, so we had to go into the actual calculus and do that to get the same sort of answers. And that's the way it'll be most of the time. Most of the time, they won't give you the graph. It's nice when they do, but most of the time they won't. Also, it's not true that the cost, revenue, and profit functions always have to be polynomial functions. It doesn't have to be true. For example, in this problem, I'm giving you a revenue function that's not a polynomial. It's x raised to a 2/3 power. The process is the same, though. It's just not quite as easy to work with non-polynomial functions. But the process is the same. You take the function, you take the derivative, so you got 2/3 times 27, reduce the power of 2/3 by 1, that gives you negative 2/3, and of course the derivative of minus 2x is minus 2. The 3's cancel, into the 20. The 3 cancels into the 27, leaves 9. 9 times 2 is going to be 18. Then you've got that negative exponent, so you can put 1 over the positive. And then finally, you've got to remember that a 1/3 power is a cube root. So this is why non-polynomial functions are sometimes more difficult to work with. In theory, it's the same process. It just requires a little bit more work sometimes to get your derivatives and put them in the form you need them in. But anyway, that's the derivatives. What do you do with the derivative? You set it equal to 0 so you can find the critical numbers. Well, you might start off by adding 2 to both sides, but at some point you're going to realize I've got to get rid of that denominator. So I want to multiply both sides by the cube root of x. That will clear the denominator. The cube root of x's will cancel on the left and leave you with 18. So you end up with 18 equals 2 times the cube root of x. If you divide both sides by 2, you'll get 9 is equal to the cube root of x. And to get rid of that cube root, you have to cube both sides. You get 9 cubed. And 9 cubed is 9 times 9 times 9. And that's 729. The problem asks us to find the number of units x. They want us to find x. So I feel pretty confident that the answer to this question is 729. But if I want to bump up my comfort level and be certain rather than pretty sure, then I can actually use the second derivative test to prove to myself that it really is a max. I feel like it is, but if I want to bump my comfort level up from pretty sure to certain, I'll use the second derivative test. Well, the second derivative, you take the form of the first derivative that's easiest to differentiate, which would be right here, and take the derivative. So you get negative 1/3 times 18. That's going to be negative 6. You're going to subtract 1 from minus 1/3, and you'll get minus 4/3, and the derivative of negative 2 is 0. You want to get rid of that negative 4/3 and make it 1 over x to the positive 4/3, and then you realize when you've got a fractional exponent, the denominator is the root and the numerator is the power. So that's going to be negative 6 over the cube root of x quantity to the 4th power. Now, the only reason I'm simplifying as much as I am doing is so it'll be easy to plug in that 729. And I'm not concerned about an exact value. I just want to know whether it's positive or negative, because positive means it's concave up, which is a minimum. Negative means it's concave down, which is a maximum. I'm hoping 729 is a maximum, so I hope that's a negative number. But if you think about it, obviously it is. The denominator is a cube root of a positive number raised to the 4th power. That's positive. The numerator is negative. A negative over positive is a negative number, and that in fact does prove that 729 is a max. The work I did in that box is just something to increase my comfort level, to say, you know, I'm pretty sure 729 is the answer. Now I'm 100% certain. So 729 is the number of units that you can produce to maximize your revenue. Start looking at the flow of things and how a lot of these problems have commonalities. The steps are relatively the same as you go through them. How about this? To study the effects of production levels on cost, one method economists use is the average cost function, as defined here. You recall, we've worked at least one problem where we referred to average cost. I don't think I used a symbol for it, but we did talk about it. Here, if you see that capital C with the little line segment above it, that's read C bar. And whenever you take a variable and put a little horizontal line segment above it, that's a symbol for average. So when I called it average cost before, I never gave it a symbol, but the symbol is to take the variable and put a little horizontal bar above it. So C bar is the average cost, and all it is the same thing as when we worked the average cost earlier. You take the total cost and divide by the number of units. So it's capital C over X. Average cost is total over X. You just need to learn that. Here's the problem. A company estimates that the cost in dollars of producing X units for product can be modeled by C is equal to X cubed minus 6X squared plus 17X. Find the production level that minimizes the average cost per unit. Not minimize cost, but minimizes average cost. So we've got to find the average cost function before we can minimize it. Well, the average cost is just the total cost divided by X. Now that's the function we want to take the derivative of. You could just use the quotient rule on this, but that would be really the hard way to do it. Whenever you've got a polynomial divided by x, the easiest thing to do is just to break it up and divide the x into each piece. So if you take x cubed and divide by x, you get x squared. If you take minus 6x squared and divide by x, you get minus 6x. And if you take 17x, divide by x, you just get 17. This is by far the easiest way to write it, so that now you can take the derivative. Well, the derivative is simple. It's just 2x minus 6. What do you do with the derivative? Set it equal to 0. Solve for x. You get 3. I'm pretty sure that's going to be the answer. If I'm not certain and I want to be certain, I can use the second derivative test, but I'm going to just go for it and assume now. I've done enough of those for now. Just go ahead and assume that's going to be it and answer the next question. The next question is, at this production level, show that the marginal cost and average cost are equal. Well, I just did the average cost. That's what I just calculated. So they want to know what the average cost is at this current production level. We just found 3. So they're asking us now to take the average cost, plug in 3, and see what happens. If you plug 3 into the average cost, you get 8. And they want to know now, what if you take the marginal cost, do the same thing, do you also get 8? They want to show that you get the same answer both times. So we have to compute the marginal cost. Well, what is marginal? Recall, marginal means derivative. So the marginal cost is the derivative of the cost function, not the derivative of the average cost. The marginal cost is the derivative of the cost. So now we have to go back to the original cost function and take its derivative. Marginal cost is the derivative of the cost function. So if you take the derivative of the cost function, you'll get 3x squared minus 12x plus 17. And they want us to plug 3 into that and see if we get the same thing. So if you plug 3 into the marginal cost function, yes, you do. You get 8 as well. So they are equal. So they just ask us if marginal cost and average cost are equal at the production level that we found in the previous question. So we took them. We had the average cost, we plugged in 3. We had to calculate the marginal cost, but when we found it, then we plugged in 3. And lo and behold, they both came out to be 8. And that's what they asked us to verify. Good little bit of work, but none of it is difficult. Just have to be careful, take it one step at a time, read the problem carefully, make sure you're answering the question that's being asked. Let's bump this up a little bit now, and let's look at some problems where they give you the setup, but drawing a picture on your own is extremely important in solving. And you're going to find a lot of these problems with optimization. If you can sketch out a little graph of something, a picture of what's going on, you'll be better off. Let me illustrate that through an example. Find the length and width of a rectangle that has a perimeter of 68 meters and a maximum area. Now these problems are all going to flow into the same sort of framework. So just be careful as you go through there and sort of learn the structure of how to solve these problems. And as you get a new problem, see how it fits into the structure. So the first thing you're going to want to do is draw a picture of what they just said. They talked about a rectangle, so draw a rectangle. They talked about length and width. If you want to use L and W for length and width, that's perfectly fine. I chose to use X and Y. But that's just my choice. It doesn't matter. Now what? Well, they told us they want the maximum area. In other words, they want to take the area function and maximize it. Well, what is the area of a rectangle? It's length times width. Well, I used X and Y, so the area of that function, which represents the area of the rectangle, is X times Y. That's the function that they want us to maximize. Well, if you got a function you want to maximize something, you normally say, well, okay, I'll take the derivative. But there's a problem here. This function has X and Y in it. So here's the general strategy. When you've got a function you want to maximize or minimize and it has two variables in it, what you want to do is go back into the problem and read it again and find some information that tells you how X and Y are related to each other. And once you find that, then you can solve for Y and plug it back into the original equation and get rid of the Y. So that's your general strategy when you're finding a function that you want to maximize or minimize. It has an X and a Y in it. is to find more information to allow you to eliminate the y. So let's go back into the original problem and see. There's some information that we haven't used. It says the perimeter is going to be 68 meters. Well, what's the perimeter of a rectangle? It's just the sum of all the lengths of the sides. Well, there are two x's and there are two y's, and it's supposed to add up to 68. So you get x plus x plus x, x plus x plus y is equal to 68, or another way of saying that is 2x plus 2y is equal to 68. I think I've said this before and probably said it multiple times. Whenever you see an equation that has a common factor, life's much easier if you eliminate the common factor. I notice there's a 2 in everything. I'm going to divide through by 2 and make life easier on myself. So what that really says is that x and y have to add up to 34. At this point, don't get lost in the weeds. What am I trying to do? I'm trying to figure out what y is in terms of x so I can go back to the original equation and get rid of the y. So at this point, I want to figure out what y is in terms of x, so I subtract an x from both sides, and lo and behold, I've done what I set out to do. I found out what y is in terms of x. But why did I do that? I did it so I could go back to the original equation and get rid of the y. So now that I know that y is 34 minus x, I got to go back to the original equation and get rid of the y and put in 34 minus x. Now I've done what I set out to do. I've gotten rid of the y in the equation for the area. That's a product, and it's an easy product, so I'll go ahead and multiply it out. That's 34x minus x squared, and that's the equation that represents the area of that rectangle. And I want to maximize it. When you maximize, you want to take a derivative. Now that we've gotten rid of the y, we're ready to take the derivative. So you do a prime. That'd be 34 minus 2x, set it equal to 0, solve for x. It turns out to be 17. I feel confident that that produces a maximum area when x is 17. But if I want to increase my comfort level, I'll do the second derivative test. The second derivative, if a prime is 34 minus 2x, the second derivative is just the number minus 2. Well, that's minus 2 is 0 for anything. Minus 2 is just a constant. It's always 0. So that function it's got negative concavity everywhere. Well, if it's got negative concavity, the second derivative test says it's a maximum. I was pretty sure it was going to be a maximum before I did the test. That just increased my comfort level from pretty sure to certain. But now that I know that's 17, I can continue on with the problem. I found x, I need y. Well, how do I find y if I know x? Well, there you go. Y is 34 minus x. I know that. So I just take my 34 minus x, plug in 17. Well, 34 minus 17 happens to be 17. So it turns out that if I want to maximize the area of a rectangle with a perimeter of 68, I can just make it a 17 by 17, which turns out to be a square, and that will maximize my area. So to answer the question, the length and width of that rectangle would be 17 by 17, which means the rectangle is actually a square. I can ask other questions. I could say actually, well, what is the maximum area? Well, once you know it's 17 by 17, you know the area of a square is length times width, because you could just say 17 times 17, but you could also just glance up here and say that the area tells you it's going to be 17, 17. And so the actual area will be 289 square meters. You can see how similar these problems are in terms of step by step by step. Each one has its own little twist to it, but the basic structure, basic logic, the basic way you work your way through these are all the same. How about this one? It says find the length and width of a rectangle that has an area of 64 square feet and a minimum perimeter. The last problem, we were maximizing area given a certain perimeter. This time, we're minimizing perimeter given a certain area. Sort of the flip side. Starts out the same though. Draw a picture. You've got a rectangle. If you want to use L and W for length and width, that's fine. I used X and Y. What am I trying to do in terms of optimization? Well, the problem says I want to minimize the perimeter. I want the minimum perimeter. Well, what's the perimeter? Add up the sides. Well, there are two X's and two Y's. So the perimeter of that rectangle is 2x plus 2y. But now I'm in the same boat that I was in the previous problem. I've got a function I want to minimize, but it's got x and y in it. What do? I look back to the original problem and find some additional information that allows me to solve for y in terms of x, and then I can substitute and get rid of the y. So I'm going to do that. What else in that problem tells me something about how x and y are related? Well, there you go. It says the area is going to be 64 square feet. What's the area of a rectangle? Length times width. So that tells me that x times y is equal to 64. Why did I do that? I did that so I could figure out what y is in terms of x. Well, I've practically done it now. All I have to do is divide both sides by x, and I find out that y is equal to 64 divided by x. Don't get lost in the weeds. Why do I solve for y? So I could go back and plug in that value in the original equation that I want to maximize or minimize and get rid of the y. Well, I can do that now. So if I plug 64 over x in for y and simplify, which simply means it's like 2 times 64 and 1 times x, I get 2x plus 128 over x. I know I'm going to be taking the derivative next, so I probably want to write that over x as x to the minus 1. So I end up with p equals 2x plus 128x to the minus 1. That's in the perfect form to take the derivative. So I take the derivative. P prime is 2 minus 128x to the minus 2. I probably want to get rid of the negative exponent, so I'll drop the x to the minus 2 down in the denominator. Then I want to set it equal to 0. You probably want to clear out the fraction so you can multiply both sides by x squared. That'd be 2x squared minus, and when you multiply x squared times 128 over x squared, the x squareds cancel and you just get negative 128. And of course, 0 times anything is 0. Now I want to solve, so I move the 128 to the other side and divide by 2. That gives me x squared is equal to 64. So technically the answer is plus or minus 8. But remember, this is a problem talking about x being the length of a side of a rectangle. Doesn't make sense to talk about a negative length. So you can throw out the negative solution because it doesn't make any sense in the context of the problem we're working. So the only critical number we care about is x equal to 8. I feel like that's going to be the value that gives me the minimum perimeter. But if I want to go from pretty sure to certain, I can use the second derivative test. So you take the second derivative, change it back to a positive fractional exponent, and plug in 8. Well, when you plug in 8, you get a positive over positive. That means your concavity is positive. Positive concavity means you have a minimum. And I thought it was going to be a minimum, but now I've gone from pretty sure to certain. So that, again, that box to work is just something to increase my comfort level from pretty sure to certain. So x equal 8 is the value that will minimize perimeter, but I need y as well. So if x is 8, all I've got to do is plug 8 into the equation that says y is equal to 64 divided by x and find out that y is also 8. So it turns out that the rectangle of area 64 that minimizes the perimeter is an 8 by 8 rectangle. And as before, I could also ask, what is that minimum perimeter? And you could just say you got 8, 8, 8, 8, it's going to be 32, or you can think of it as actually plugging 8 in here and 8 in there. When you plug it in anywhere that says P, in any case, you're going to get 32. If you plug it in here, you get 8 and 8, you get 32. If you plug it in here, you get the same thing. Anywhere you plug it in where it's P is going to give you the same value as 32. So if you want to find the length and width of a rectangle that has an area of 64 square feet and a minimum perimeter, you'll end up with an 8 by 8 rectangle with an area, with a perimeter, of 32 square feet. And again, notice that even though the problems are different, one of them, the previous one gave you a perimeter and wanted you to maximize area, and this one gave you an area and minimize perimeter. The flow of the problem the flow of the problems are remarkably similar to each other. How about this one? Pam plans to build a rectangular pen for a pet against the side of her house. She wants the pen to enclose an area of 8 square meters and no fencing is required along the side adjoining the house. What dimensions will use the least amount of fencing? Pam wants to save money and not spend any more on fencing than she can get by with and still have 8 square meters of space within the pen. First thing, draw a picture. It's built against the side of the house, so you really only need to make a 3-sided fence. You only need fencing material for 3 of the 4 sides because the house blocks the 4th side. You don't need fencing there. So what do we want to do? We want to label, and I decided I'd use X's and Y's again. You can choose whatever letters that make sense to you. But what am I trying to do? I want to use the least amount of fencing. So I used capital F to stand for fencing. And I'm counting. There are 2 X's and 1 Y worth of fencing. So that's 2X plus Y. If I needed 4 sides of fencing, it'd be 2X plus 2Y. But since I don't need fencing on that 4th side because it's up against the house, the fencing is only going to be 2X plus 1Y. Again, that's the function I want to minimize, least amount, but it's got X and Y in it. The strategy when you have the function with 2 variables is to read the problem again and find some information that you can use to relate X to Y, and then you can solve for Y and eliminate it from the original equation. So I'll read back up there and notice that it says that the area has to be 8 square meters, and the area of a rectangle is length times width. Well, that's X times Y, and I want it to be equal to 8, which means if I divide both sides by X, that Y is just 8 divided by X. Why did I do that? So I could plug in the original equation and get rid of Y. So I take the 8 over X and plug in for Y, and I get F is equal to 2X plus 8 over Y. I know I'm going to be taking derivatives, so I want to write that 8 over X as 8X to the minus 1. Now it's in the perfect form to be differentiated, so F prime is 2 minus 8X to the minus 2, which of course is 2 minus 8 over X squared. I want to set that equal to 0. Clear the fractions by multiplying both sides by X squared. That gives me 2X squared minus 8 equals 0. Move the 8 over, divide by 2, you get X squared equals 4. That means you get technically plus or minus 2, but remember these problems, the variable represents the length of a side of something, so it can't be negative. Negative doesn't make any sense. You're only interested in the positive critical number in this particular context. Again, I'm pretty sure that's going to be the minimum, but if I want to go from pretty sure to certain, then I take the second derivative, plug in 2, and notice that I get a positive answer. Positive means concave up, means holding water, and that means it is in fact a minimum. That just takes me from pretty sure to certain. I was pretty sure it was going to be 2, so I'll go ahead and label the 2 in the diagram. I need to find out what Y is. Well, if I know X and I want to know Y, I just plug that X into the relationship between X and Y. Well, if X is 2, 8 divided by 2 is 4, that means Y is 4. So the answer to the question, what dimensions will use the least amount of fencing, it would be a 2 by 4 set of fencing where the length 2 were the side that are perpendicular to the side of the house, and the 4 is the fencing that went along parallel to the side of the house. And were they to ask me what the actual amount of fencing would be, you just add them all up. You got 2 2s and a 4. That'd be 8 meters. It would take, you'd have to go to Lowe's or Home Depot or wherever you went and buy 8 meters of fencing to do this job. Again, think about the commonalities and what you're doing in common to all these problems. Lots of similarities when you work problem to problem. Let's jump now from 2 dimensions to 3 dimensions. This problem increases the dimensionality. It says an open box is to be made from an 18 by 18 inch square piece of material by cutting equal squares from the corners and turning up the sides. So you've got picture a square piece of cardboard or a square piece of plywood, you're going to cut out those corners x by x, and then you're going to turn up the sides. I guess it's better to think of it as cardboard because you can think of that as folding up. And what question we want to answer is this: find the volume of the largest box that can be made from that particular piece of material. The volume of a box. Well, you need to be able to picture that box in your mind or actually draw it out on paper. So what you're doing is you're folding up those sides once you cut out the corners and making a box out of it. So you'll get something like that. The 18 minus 2x dimensions stay on the ground, stay on the table, wherever you're doing the folding, and they become the base of the box. And the x by x squared that you cut out, that x becomes the height of the box. It says it's an open box, so there's no top on it. Well, what's the volume of a box? Well, and also, by the way, once you get the box in there, you can get rid of the original picture once you've got the box if it's distracting. But once you get that, how do you find the volume of a box? Well, it's just length times width times height, and we know that the length and width are both 18 minus 2x, and the height is x. If you multiply everything out and just make it into a polynomial, that's probably the best way to do it. So you do FOIL method on that polynomial. I won't belabor that. You'll get 324 minus 72x plus 4x squared multiplied by x. And if you multiply through by x, you'll get 324x minus 72x squared plus 4x cubed as the volume. Now, I went ahead and put the volume up here inside the box because I'm going to erase some of this later to make more room, and I want that volume formula to stay there. But now I'm ready to take the derivative. Well, the derivative of 324x is 324, and so on and so forth, and you get the derivative. Now, I know I'm going to set it equal to 0, so I'm probably going to have to factor that. It's just a matter of preference. You can leave this just like it is, but I sort of like the square term to be first. I'm used to seeing it that way. You don't have to rewrite it, but I feel better if I do. So I just put the 12x squared first and wrote it in decreasing order. That's just a matter of personal preference. But I know I'm going to set that equal to 0. So I might as well go ahead and factor it. And I notice that there's a 12 inside of everything. I always look for common numerical factors too. There's a 12 in each one of those. So the 12 can be factored out, and you get 12 times the quantity x squared minus 12x plus 27. And now if you try to FOIL factor that out, you'll find out that that does indeed factor. And you get the derivative as 12 times x minus 9 times x minus 3. So now when you set it equal to 0, you'll already have it factored. You can set it equal to 0 and then factor, or you can factor and then set it equal to 0. That's sort of irrelevant. But when you set that equal to 0, you can see you're going to get a critical number of 3 where that factors 0. You're going to get a critical number of 9 when that factors 0. So there are two critical values. And keep in mind, I want to find the largest box. I want to maximize. So I need to figure out, I'm assuming one of those is going to be a maximum value. So how do you test it? Well, we've done this several times now. Take the critical numbers and use the second derivative test. Before, it was just sort of a matter of comfort level. I want to go from pretty sure to certain. Here I've got two possibilities. I really need to do the test here. It's not a matter of comfort level. I just don't know which of those is the max. So I really do need to know here. And remember, we found the derivative and wrote it in several, I'll show you. I wrote the derivative in several different ways. You want to pick the version of the derivative that's easiest to differentiate. In my opinion, that's the easiest form to take the second derivative from. So that's the form I'm going to choose. So once I have that version of the derivative, I'm going to now take the second derivative, which is easy enough. I get 24x minus 144. Plug in 3. Do the arithmetic. You come out with negative 72. Remember, negative second derivative means that you're concave down. And if you're concave down, that means you have a relative max. And that's what I was looking for. I was looking for the largest box. I'm looking for a max. But I do need to make sure the other one really is a min. I don't want to get into a situation where I have two maxes and I've got to figure out what's going on there. So I'm going to check that 9 and see. If I plug 9 in, I get positive 72. Well, that's a concave up region, which is a minimum. So that's not the one I'm interested in. I want the largest box. That's the max. So I want the max one. The max one's the one I'm interested in. So now I know. X equals 3 gives us the max volume. The problem, though, it didn't ask for X, and it didn't ask for X. It said, what is the volume of the largest box? So X equals 3 is not the answer to the question. It's something I have to go get to get the answer, but they actually want what the volume is. So I have to go back to my formula for volume, and I'll pull it back from earlier work. Oh, here it is, right there. And plug 3 in, and if you plug 3 in for X, I'll let you do the arithmetic, but you come out with 432. So the question didn't ask for X this time, it asked for the actual volume. So the volume of the largest box that you can make out of an 18 by 18 inch square piece of material by cutting out those corners is a 432 square, what are my units? Square inch volume. Again, look at the commonalities between all the problems we've been working and how much in common these solutions have with each other. How about this? A rectangular solid with a square base. So we got this time we know the base is square. It was actually square in the last problem too. It doesn't have to be, but these problems have both said we have square bases. It has a volume of 1,728 cubic inches. X is the length of the sides and H is the height, so I've labeled it that way. Question is, find the dimensions in inches that yield the maximum surface area. Well, volume, we pretty well knew that, but what is surface area? Think of it this way. The surface area is basically just the amount of material, in this case square inches of material, you need to build this thing. Also be careful here. This is a rectangular solid. It doesn't say anything about an open box or anything. So this thing actually has a top and a bottom. So it's a little different than the last problem that it was an open box. This one's solid. It has a top and a bottom and 4 sides. But what is the surface area? We've got to find the surface area formula or we can't minimize it. So let's go off to the side. Let's just forget about all the words we just read. Let's just concentrate on finding a formula for the surface area of this box. Remember, the square base, X and X, and height H. I just went ahead and put a label on every one of the sides so we can see better. So we're looking at how much material you'd have to buy if you went to Lowe's or Home Depot's. How much material would you have to buy to build this box? Well, think about the area of the base is a square. It's X by X, and I sort of colored it in so you can see the base of this thing has an area of X squared. But this thing also has a top. But if you start off, you're adding in, that's the area of the base. We're building up our surface area formula, and so far I've only got the base, the area of the base in there. But I know that the top is also X by X, so I got to throw in another X squared. So this is the bottom, this is the top. But then I've got 4 sides, but each side is X by H. So the area of a side is X by H. So that's a side. But there's more than one side. There's actually 4 sides, and I've only written down 1, so I have to put 3 more in there. So these are the 4 sides. So the surface area formula, let me clear off some of my scratch work here. The surface area formula there are 2 x squares and there are 4 xh's. So the surface area formula is 2x squared plus 4xh. So that's what I'm trying to minimize. So now that I've got the surface area formula, I can go back to the original problem and write down the formula. That's what I'm trying to minimize. Minimize surface area. How do you do it? Well, as before, we've got an X and an H. It's been X and Y. It doesn't matter. There are 2 variables in it. There's an X and an H. We need to get rid of that H. How do you do that? You go back to the original problem and read through it and find some additional information that relates x and h together and use that to solve for h and then eliminate the h in the thing you want to minimize or maximize. So rereading the problem, what do? I realize they tell me something about the volume being 1728, and I know the volume of a box is length times width times height. And in this particular problem, that's x times h, and they tell me that it's supposed to come out to be 1728. Well, x times x is just x squared, so x squared times h is equal to 1728. I want to solve for h so I can get rid of the h in the other equation, so if I divide both sides by x squared, I find out that h is 1728 divided by x squared. And again, don't get lost in the weeds. Why did I do that? So that I could go back to the original function that I wanted to minimize and get rid of the h. So I plugged 1728 over x squared in place of h. And again, let me get some of this scratch work I did out of the way. And then you want to simplify it, of course. And if you simplify that, you want to get rid of that over x and make it x to the minus 1, because I know I'm going to have to differentiate it, and that's the easiest way to differentiate it. Now it's ready to be differentiated. If you take the derivative of 2x squared, you get 4x. If you take the derivative of 6912 x to the minus 1, you get minus 6912 x to the minus 2. Now that I've taken the derivative, I want to put it back into the right form, so I want to take that x to the minus 2 and write it as over x squared. Then I want to set the derivative equal to 0. It's got a denominator, so I want to multiply through by the denominator to get rid of all the fractions. So I multiply through by x squared. That gives me 4x cubed minus 6912 equal to 0. Move the 6912 over, divide by 4. So x cubed is 1728. So x is the cube root of 1728, and that comes out to be 12. So I'm pretty sure then that the area of the base is going to be, the dimensions of the base is going to be 12 by 12. I'm not going to go through the test. If you wanted to be absolutely certain, you could do your second derivative test. I've done it several times. I'm not going to do it again here. But if you wanted to be absolutely certain, you could. I'm just going to go ahead and assume that if I did it, it would come out to be a minimum. Earlier, we found out that x was, well, you can see where we got it here. H. H was 1728 over x squared. So once I know x, all I got to do is plug it in. I'll know h. Well, 12 squared is 144, and 1728 divided by 144 actually comes out to be 12 as well. So the question was to find the dimensions that yield the minimum surface area. So the dimensions, you see them on the box, are 12 by 12 by 12. So a 12 by 12 by 12 box, rectangular, solid, whatever you want to call it, keeping in mind that it has a top and a bottom, would minimize the surface area. If they were to ask what the surface area was, all you'd have to do is go back to the surface area formula and plug in 12 for x and 12 for h, and you'd find out that the minimum surface area would be 864 square feet. Please work through these problems seriously and thinking about every step as you go and noticing how similar the steps are from problem to problem. Everyone has a little twist to it where you have to do something slightly differently, but the basic processes are the same in problem after problem after problem.